Hello, should I start?
So we are back, and sorry for this slight delay. We were just getting the technology adjusted. It's my great pleasure to chair this next session. The next speaker is Nizar Touzi, and as we all approach retirement age, we want to know if there is a golden parachute in our principal agent problem, but let's see if there is one in Sannikov's problem. Nizar, all you.
Okay, thank you very much, Mateus. Okay, it's the first time I'm presenting on this Google Meet app, so I hope everything will go well. So as Mateus said, this is actually. Oh, there is an echo. I don't know why. Okay, so this is a paper about one of the one of the main papers in principal agent problem, contract theory, which was part of the PhD of Yuri Sannikov, and actually it is a very important paper in the literature. Many people are following this paper, and personally, I got to this field through this paper because I try to understand what's going on, and for a long time I tried to avoid to understand details in the paper, and it took us some time to make it the framework work well, rigorous, etc. And then, like last year, just before the confinement, I went back to this paper because I wanted to understand this particular example. And it turned out that I could not understand. So it took me a lot of time. And I got to work with Dylan again on this problem. And hopefully now we can understand all the details. And we can explain some of the results in Sannikov's paper, and actually correct some others, as I will show you, because there are some claims which do not hold. Okay, so this is the problem which was introduced by Sannikov. It's a optimal incentive type of problem. A situation of interaction between two agents, one of them, two actors, let's say two actors. One of them is called agent, the other one is called principal. Principal is the boss, so has a priority on the agent. So principal has a project with production process of the product, which is called output process, is the process xt. So this is the dynamics of the process xt is given here by this equation, where you see that the management of this output is delegated to the agent. So principal is the boss, he has the checkbook, he only writes checks, but the agent is in charge of working for the project, of managing the project, and by devoting the effort alpha in red, by devoting effort alpha, the agent is able to impact the average return of the output process. And in this problem, there is an observability problem. The principal cannot see this effort because the effort is hidden behind the Brown emotion. So if X reaches high values, the principal doesn't know if this high value is due to good effort from the agent or is here by luck because nature was good to us. So that is the basics of this model. There is an information asymmetry. The agent devotes effort, which is not seen by the principal, but the principal sees the overall impact of the effort, the realization of the output process X, and based on the realization of X, should decide how to pay the agent in order to incite him better for the management of the output process. So the problem as formulated by Sannikov is an infinite horizon problem. the agent given a contract. So the contract in this situation is the stream of payment, pi s, the stream of payment promised by the agent. So it's a parameter given to the agent. It's part of the contract. So the contract is how much is the agent is going to earn at each point in time. And given this pi, the agent is going to maximize utility, maximize this expected utility, and return an optimal response, alpha. So how much effort the agent is willing to put in the project, given that the payment structure is pi s, so pi will be a function of x in here, and given that the effort is costly for the agent, so h is a cost function, is a cost of effort function, so typically h of 0 equals 0, and h is an increasing function. Okay, so this is the agent problem. So given pi, the agent returns an optimal response alpha hat of pi. Alpha hat of pi is the optimal response of the agent. Now the principal has her utility function here, expected value. So the principal takes as given the optimal response of the agent. So given the optimal response of the agent, the gain of the principal is the earning from the production asset, dxt, minus whatever promised to the agent, minus pi tdt, and everything is discounted with the interest rate R. Sannikov is using the same interest rate, but we'll see later that we can handle different discount rates for both actors. So from here you see that dxt, if we replace dxt by alpha tdt plus sigma dw, the stochastic integral part vanishes under expected value, and we are left with alpha hat t minus pi tdt. So whatever average income is produced by the agent, alpha t, is taken over by the agent, alpha hat t. And so the principal wants to maximize her criterion by choosing the best contract to offer to the agent. What is the best contract that principal can offer to the agent so as to incite the agent to work in the good interest of the principal while being happy, while maximizing his utility? In this problem, there is the so-called participation constraint, which plays an important role, and which is written here. Without this participation constraint, we would be in a situation of slavery, because the principal may impose a negative payment to the agent. Negative payment, so would take benefit from the negative payment to the agent, and the poor agent would have no choice but responding to a large negative payment, probably would devote the worst effort, even negative effort whatsoever, the worst effort, but the principal would not care anymore about this situation, because the principal would be taking benefit from the pi and not from the alpha hat. And notice that in Sannikov's problem, the set where controls take values is this set A, which is assumed to be bounded. This is the only condition assumed on A. It's a subset of the positive real line, which is closed bounded and contains 0. So it is legitimate for the agent to devote 0 effort. Okay, so this is the problem which was formulated by Sannikov, and let me go and tell you what are the results which were found by Sannikov. So I'm going to go fast on this. Maybe I should explain this definition. What is a golden parachute? A golden parachute is a situation. Okay, let's forget about these notations because I want to save some time. So what is a golden parachute? A golden parachute is a situation where the agent does not make any effort. So alpha equals 0. We set alpha equals 0, then h of 0 is 0. Suppose from time capital T on, forever, after time capital T, alpha equals 0. So this is situation of retirement. This is the situation of retirement. As the agent is not making any effort, is not working. Agent is not working anymore, but pi s is a constant over throughout from capital T on up to infinity. So you see that if you integrate u of a constant from capital T to infinity, this is just u of the constant integration of r e to the minus rs, but the integration of r e to the minus rs up to infinity is exactly 1. This is the reason there is r here, factored out. So in this situation, if such a contract is optimal, this means that there is some possibly random time, stopping time, typically will be stopping time, but which is not defined clearly in Sannikov's paper. This is one of the reasons why the paper is difficult to read. So there is possibly some random time after which the agent do not devote any effort while still being paid some constant payment forever. And this is what he calls, this is what Sannikov calls golden parachute. This is a situation of golden parachute. And so one main feature of this paper of Sannikov is to discuss whether a situation of golden parachute can be optimal in a principal agent problem like this one. Okay, and the main finding from Sannikov is summarized in this slide. There are some conditions. Utility function of the agent is C1, strictly concave increasing, u of 0 equals 0, and u prime at infinity equals 0. Okay, so very large class of utility functions. Some conditions on the cost of effort. H is the function of cost of effort. C1 increasing strictly convex, and the marginal cost of effort at 0 is strictly positive. This is an important condition in his paper. Marginal cost of 0 is positive. It's the only non-trivial type of condition. So what Sannikov does, Sannikov shows that the principal problem is a solution of some ODE, which is kind of AJB equation. I will explain later what is this equation exactly. And this is also was difficult for us to understand and generated a lot of work to justify this how to convert the problem into a control problem. So Sannikov shows that there exists a solution V to the AJB equation of the principal problem, so that the principal problem VP can be expressed as supremum over solutions of this AJB equation over all y0 greater than capital R. Capital R was our participation constraint. Capital R is the participation constraint of the agent. And what Sannikov shows is that for small y0, there is always informational rent. So this function V is like this, is a function which has this type of behavior, which means that if y0 is smaller than this maximum value of this V function, then participation constraint, if the participation constraint of the agent is smaller than the location of the maximum, then it is optimal for the principal to give strictly more utility to the agent, which is very favorable to the agent. This means that by hiding his effort, the agent is able to get strictly more than what he asks for. He asks for R, and he gets strictly more than R. He gets strictly more than R. So this is a remarkable result. This is one remarkable result. And the other important result of Sannikov is that there is always golden parachute. There is always golden parachute is always optimal. Golden parachute is always optimal. I thought it would be written in this slide. There is always golden parachute in this. Golden parachute is always optimal. So what I will show you in the few minutes that are remaining is that we can have a rigorous formulation of this problem now, that it is not true that golden parachute is always optimal. Golden parachute may be non-optimal. The information rent at origin is always true. Actually, we have a necessary and sufficient condition, but which is always true under the conditions of Sannikov. And we also can allow for different discount factors, which introduces a new feature. At least for me, I have never seen a feature like that in control theory. There is some kind of boundary layer in an optimal stopping problem. I have encountered many times in many works the boundary layer because of singular control, singular stochastic control, but here we have boundary layer in an optimal stopping problem, which kind of new to me. Okay, and this also contrasts with some conjectures in Sannikov. Sannikov does not address the problem with different discount factors, but provides some intuitions and some conjectures about that case, and it turns out that some of them are shown to be not true or true. Okay, depending on them. Okay, so the formulation that I will propose is the following. Now I would like to emphasize on the fact that the contract has three components. I would like to emphasize that at some stopping time tau, which is announced in the contract, the agent can be retired by the principal. So the principal says it very clearly in the contract. Under some conditions on the output, retirement will happen. This is tau is a stopping time in the filtration of X, in the filtration of the output. Pi is as before. This is the continuous payment. And what I call Xi. Xi is a final payment at retirement. So now in this situation, golden parachute would be a very clear situation where optimal stopping time tau star is finite. So there is an optimal time where the agent is retired. And the Xi, the probability that Xi strictly positive is strictly positive. This is a situation of golden parachute. Okay, there are some technical conditions. I need also to introduce some conditions, some growth conditions on the utility functions to put everything very rigorous. So I want the utility function to behave at infinity like a power function. At infinity, it should behave like pi to the power 1 over gamma for some gamma greater than 1, like a power function. But in between time, it can be quite general. But at infinity, we needed to have this type of behavior. I will also introduce discount factors, which are different for the agent, for the principal, R for the agent, and rho for the principal. And in the next slide, I will denote delta, the ratio R divided by rho. Okay, now the contracting problem is very similar to the formulation of Sannikov, but now, as I said, I want to emphasize that there is a termination time tau, which might be finite. So at time tau, the tau is a retirement of the agent, a retirement time of the agent. When retired, the agent gets the benefit Xi, so utility U of Xi, and has the continuous payment U of pi minus h of alpha ds. This is the cost of effort part. And the principal now has this utility function, similar as before, except that now tau is explicitly written here, so pays C to the agent, so discounted with different discount rate rho, and also pays the continuous salary minus pi. Again, the problem is the same. Agent maximizes utility given the contract offered by the principal, C, boldface phi, given boldface C, and returns the optimal alpha hat, which might be multiple optimal responses alpha hat in some set A hat of C. Now the principal's problem is find the best contract, find the best C. Now C has three components again, Xi, tau, and pi. Find the best contract so as to maximize her utility function, which is given here. And in case there are many optimizers, many optimal responses from the agent, we assume, as usual in the economic literature in this subject, in this topic, that the agent collaborates with the principal. So in case the agent is indifferent between many strategies, he would be willing to follow the best strategy, best in the point of view of the principal. And again, this participation constraint. Okay, so once we formulate the problem like this, then we can, well, first, there is a so-called first best formulation of this problem, where the principal has full power, in the sense that the principal can decide, first observes the effort, and can decide about everything. What is the best contract? What is the best effort to be devoted by the principal? This is formulating this problem, so the principal maximizes her utility over C and alpha. So the principal can decide immediately what kind of effort should be put by the agent under the constraint that the agent accepts. In this situation, what we can prove, this calculation is not difficult. This is just, now this is a standard optimization problem, while the previous one, while this problem is a Stackelberg game problem. In this standard optimization problem, what you can prove is that there is no golden parachute. NGP stands for no golden parachute. So golden parachute is not optimal. So the optimal firing time or retirement time is plus infinity in this problem. So from this point of view, you see that the second best situation, or the situation where the agent can optimize on her own, is a favorable situation for the agent. Okay, so again, the contracting problem, there is a small transformation of this problem is to change coordinates. Instead of writing U of Xi for the salary, for the retirement parachute, golden parachute taken by potential golden parachute earned by the principal, let me call it zeta is U of Xi.
Nizar?
So there is this change. Yes?
5 minutes, okay?
Okay, thank you. So I call this, so this introduces this function f, which naturally comes up here to modify just an equivalent formulation. Instead of maximizing over Xi, now I'm going to maximize over zeta. But naturally, there is minus the inverse of the utility function, which comes up, and we are led to this formulation for the principal. For the principal now, the utility function only shows up in the principal problem, f of zeta and f of eta. Now, what we can prove is that first, there is this function f bar, the so-called face-lifted inverse utility function. So we have to move from f to f bar first. It is optimal to move from f to f bar. And under this change to f bar, the principal problem becomes supremum, is equal to the supremum of criterion j bar. And in this criterion j bar, the f is turned into f bar. So what is the interpretation of f bar? F bar is, the interpretation is that when retirement comes up, the principal may think that maybe it's better to pay a constant payment forever instead of retiring the guy immediately. So this is the meaning of this control problem. So the principal chooses the best way to implement retirement. This is this f bar function. Now, given this f bar function can be computed almost explicitly in this example, at least through its convex duality function. F bar star is explicit in terms of f star. Okay. Now, the main result is that first, there is a reduction of the principal problem into a standard control problem. So this, again, this is following the idea of Sannikov. So the only thing that we bring in here is to make the full story rigorous. So this is the bright idea of Sannikov, that this problem, this Stackelberg game problem, can be converted into a stochastic control problem where there is no game feature, and where the state variable becomes this y variable here, which in fact turns out to be exactly equal to the continuation utility of the agent. So this can be proved rigorously, and this is what we get. And once we arrive here, we can handle this problem by standard stochastic control problems. Okay, so we have this controlled variable y, which is controlled through the z here. Diffusion is controlled by z, and the z has an impact on the a hat, on the drift as well, because a hat is an optimal response. A hat is in a hat of z, this capital A hat of z, set of optimal responses. Okay, now you take this control problem, you write the Bellman equation of it, you get an obstacle problem because there is both optimal stopping and optimal control. This is the equation for it. And this equation turns out to be very difficult to analyze. This is where we had a lot of trouble to prove existence and uniqueness for this equation. Well, first, there is only one boundary condition, while it is second order ODE, in fact. And second, there is this F star, which is highly explosive. Anyway, I don't have time to say more, but let me tell you, first thing is that we can prove that our main result is to prove existence and uniqueness of a solution, which is C2, and which has this growth controlled by this function around f bar, log of 1 plus log of 1 plus y. And we can prove that this is the situation of informational rent, if and only if there is a very precise condition for informational rent. And we also have a sufficient condition to have a golden parachute. And I will finish my talk only by saying that we can emphasize some situations where there is no golden parachute. While, as I told you in Sannikov's paper, it is shown that there is always a golden parachute. So what we can prove is that there is no golden parachute, at least in the three situations which are emphasized here: beta equals 0, or beta strictly positive, as in Sannikov's paper, but the inverse utility function has this type of properties. So I function is very explicit. Or another condition of different nature is given here. Again, this H is the cost of effort, and capital F is the inverse utility, capital F bar is this face-lifted inverse utility. And if you look at these conditions, they all say somehow that beta, which is the marginal cost of effort, is big enough. Under all of these conditions, we can prove that there are situations of no golden parachute. So I will stop here. I think I'm out of my time. I will stop here. Thank you very much. I can take some questions if you have any.
Thank you, Nizar. I don't see a question from the audience yet on the YouTube. I'll just, and we are out of time, but I just wanted, if you could say in 30 more seconds, just elaborate on this last thing that you said. So the economic meaning of the situations where there's no golden parachute is that the marginal cost of effort is large enough. Is there some intuition for that, or is just what comes out of the technical?
It's what comes out from the technical condition. Like as usual in this type of conditions, you can find always justification in economics. So maybe it is saying that it's too costly to incite him at zero because this marginal cost is big enough.
Mm-hmm.
But I don't have a clear intuition about it. Huh?
Okay.
Especially that the situation beta equals zero is also a situation of no golden parachute.
Right.
So on the other side, there's also the other extreme.
Right.
It's a situation of no golden. And again, these are sufficient conditions. These are only sufficient conditions. So we don't have necessary and sufficient conditions.
Okay. Thank you very much.